Yeah.
Alright, let me share my screen actually. My well-formatted presentation
Yes.
using the default Google Slides
Looks good.
theme. I tried using other themes, but it looked really corny, so I'm like, stick with this one.
You should have used the Windows 2000 era slideshow themes with all those silly animations.
Oh
Made it
no.
as it made it as awful as possible.
Alright, I'll start for real now. So, I'm Jaker, and I'll be talking about volumetric fog. And by the way, volumetric fog is referring to a specific technique. Oh, hello. Yeah, so volumetric fog refers to a specific technique that I'll be covering today, even though it reads as a pretty generic way of rendering. The presentation is heavily inspired by Bart Ronsky's presentation, Assassin's Creed 4 Black Flag Road to Next Gen Graphics. I recommend checking it out. When I say inspired, I mean it's really inspired by that. And feel free to jump in, ask questions at any time. So why the heck do we want volumetric effects? The main reason we want them is because they look cool. And not only that, but they add lots of depth to a scene and can contribute to its mood. For example, here's a picture that I took from online. Yeah. So some games use fog to hide asset streaming as well, and chunk loading, like in Minecraft. At the edge of the world, you can see fog that kind of obscures the chunk loading a bit. And so this is from a real game. Here's my demo. Pretty much indistinguishable, I'd say. So here's an example of a scene in my demo with volumetrics. And here's what it looks like without volumetrics. Hopefully you can see some sort of difference between the two. Yeah, as you can tell, adds quite a bit to the overall mood. So I'll do a little refresher on volumetric rendering. It's pretty much like regular rendering, conceptually, except you have to integrate along every point along the ray as well. Physically, what this means is that you're computing the path every scattered ray takes and its interactions with potentially every other ray and particle in the media as it bounces through and around. So it's a bit more complicated than, uh, I guess, vacuum rendering. The phenomenon of light rays bouncing multiple times through the medium is known as multiple scattering, and it's really uh, computationally expensive to calculate, and it doesn't add that much to the final image, so we won't worry about it here. And most techniques, including the one I'm covering today, focus on the light directly entering or exiting what you can see, the black ray. I don't know if you can see my cursor, but the black ray going from the object to the eye. That's the eye ray. That's called single scattering when you only focus on that ray. At any point along any ray going through, any light ray going through participating media, such as fog, light can enter or leave in three ways. It can leave through absorption as it travels through the media and gets absorbed by tiny particles, and it gets converted to heat energy. It can also scatter out of the ray. Light can scatter out of the ray if it collides with the particle. That's called outscattering, as you might expect. And light can also be scattered into the ray from any direction, and this is called inscattering. Participating media can also emit light into the ray, just like any other material, but Usually it doesn't come up, especially when you're rendering fog, so we won't worry about
Worry
it
about
here. So one of the main components in volumetric rendering is Beer-Lambert Law, which it combines both the light loss due to outscattering and absorption for incoming light rays. So the amount of light successfully transmitted is exponential and is relative to the amount of density, uh, quote unquote, or particles that the light ray had to travel through. So you can kind of see in this fancy illustration I made, you have the light ray going from the sun to the observer on the left, and as it travels through like fog or any other kind of medium, it rapidly gets absorbed using an exponential function. Another important effect that we like to simulate in volumetric rendering, or particularly atmospheric rendering, is Rayleigh scattering, which is caused by light rays hitting tiny molecules of air, as opposed to large aerosol particles like those in fog. So Rayleigh scattering is responsible for a tiny bit of absorption, pretty much negligible, and it creates the scattering of it is what creates the blue and red color of the sky, due to it scattering shorter wavelength of light more than longer wavelength. Since this effect is only noticeable at very large ranges, it doesn't. It's not important to simulate for fog, like local fog that we see at the ground. So we don't need to simulate it for our purposes. What we do care about is me scattering, which is super important for the look of fog and clouds and smoke. It's caused by large particles in the air relative to the wavelength of light. So like water droplets, smoke particles, and so forth. The light is scattered mostly forward relative to the light vector. Um, that's called anisotropic scattering because it doesn't scatter equally in all directions. You can sort of see the effect in the clouds on the right picture here. The clouds are closer to the viewer, like the sun's like off on the top left. You can't really see it, but the clouds closer to the sun are brighter, and the clouds are farther away or darker due to the forward scattering caused by me scattering. So yeah, that's another effect that we want to, that's the main effect we want to simulate in fog. And related to it are phase functions. So the directional scattering is controlled by the phase function, which essentially describes how much light is scattered in any particular direction in participating media. So for single scattering, we only care about how much light is scattered into the eye ray, the ray that's going basically out of our eyeball for the pixel. Important property of phase functions is that they're energy conserving, which means if you integrate over it in all directions that the light could be scattered, it'll add up to 1, which means it neither creates nor destroys light, which is important if you're trying to simulate reality. And phase functions are often anisotropic, which means the amount of light scattered depends on the angle in which it is being scattered. For example, in this photo, you can see how a really complicated phase function can create a fog bow, or at certain angles away from the light, more light gets scattered back into our eye uh, as it goes away from the light source. This is a form of backscattering. A common approximation used for phase functions is the Henye-Greenstein or HG phase function. Hopefully I pronounced that right. It's a relatively cheap to evaluate and common phase function that features a single strong lobe, as you can see in this picture or the graph. It uses an anisotropy parameter g to indicate how much forward or backscattering there is. If g is 0, then the scattering is isotropic or equal in all directions, which you can see in the red circle here. So this is a polar graph which shows the scattering intensity based on the angle. So rightmost should be representing a vector that's perfectly in line with the light ray. So you can see there's more forward scattering if g is above 0. Another phase function that is often used is Schlick's phase function, which is an approximation of the Hg phase function, an approximation of an approximation, if you will. You can see both phase functions at the bottom here. It's not important to remember that, as long as you write it in code. So existing techniques for rendering volumetrics. Older games often use analytical techniques as they're based on depth or height or both. They're usually really cheap to compute, and they're relatively realistic for how much they cost to render. These days, Unreal Engine offers multiple forms of analytical fog, including exponential height fog, which decays as height increases. The main downside to this approach is that it's difficult to support varying media intensity. So if you wanted, like in the top right picture, if you wanted like a bunch of fog in one spot, like behind the sand wall or something, you couldn't really do that because the fog is entirely based on depth from the observer. So it's not very flexible in that regard. Another technique that's sometimes used in games is to just spam a bunch of billboard particles that are translucent. It required basically no programmer effort to implement, but it required a lot of manual adjustment to look good, and even then it might not look that good. I used a picture of a dust cloud volume from Source Engine, as I couldn't find a good example to use in a game. Some more existing techniques. So Crisis popularized the use of screen space, God rays, so to speak. It's an effective way to mimic fog shadowing, but it requires light sources to be on screen, and ultimately isn't a very comprehensive fog solution. If you turn around, in this top right picture, if the observer turned around, then the fog shadows would no longer be visible. On the other hand, ray marching is a technique, a numerical solution to the volumetric rendering equation, which means it pretty much supports every kind of volumetric effect, depending on how much computation you're willing to put into it. So it could support shadows, local lights, varying density at any point in space. So on a per pixel basis, it's really expensive to compute ray marching. So a lot of engines render it at a lower scale, like 1/4 or 1/16 scale, and they use a bunch of tricks, upscaling and temporal accumulation tricks to make it look good. A lot of newer games use ray marching for rendering clouds and local fog volumes, as hardware today is really powerful. And ray marching is used as the basis of the volumetric fog technique that I'm about to cover right now. So the motivating idea behind volumetric fog, the technique, is that most volumetric lighting effects are very low frequency in screen space. So if you take any two adjacent pixels in screen space and look at how much uh, fog contributed to it, the rate of change would be very minimal. And so we can use this info to know that we don't have to compute fog full resolution, or in fact, we can completely separate the idea of integrating the scattering equation into its own thing separate from the screen. So we can calculate the in-scattering and transmittance at every point in a frustum-aligned grid, and we can quickly and easily apply volumetrics to each pixel by using that grid, by projecting the screen space pixel into a grid UV and sampling the grid. I'll expand on that later. But the idea is similar to uh, clustered lighting or clustered light culling, in that you split the frustum up into cells of, yeah, you can see forward view, top-down view. I stole that picture from a clustered lighting tutorial, by the way. Oh, and the original presentation that I was heavily inspired by recommends a 160 by 90 cell volume with 64 or 128 slices. But since that was made for last-gen consoles and last-gen PC hardware, we can easily up the number of slices to 256 and still get good performance. So the first step in this algorithm is to render shadows normally in a shadow map, and then downsample and filter to create an exponential shadow map. The exponential shadow map will be used to provide soft fog shadows. And by the way, it's really hard to visualize exponential shadow map because the greatest values in it are like 10 to the 17 or something, so you can kind of see the fuzzy edges. Just pretend it's a really soft shadow map. The second step of volumetric fog, but the first real step, is to calculate the density and lighting for each cell in the frustum-aligned volume. In my demo, the density is calculated by using simplex noise for ground fog, but you can also apply any line distance function or shape you want to the fog. It's really flexible in that regard. And the lighting is calculated similarly for every cell, by simply looping over all the lights in the scene, or you could use clustered light culling to expedite it. And you multiply the light color by the fog color, accounting for Beer-Lambert law. You also apply sunlight along with the exponential shadow map to get soft shadows, which will also be shown later. The exponential shadow map is necessary as there's terrible aliasing if you use regular shadow mapping due to the low resolution nature of the volume. So if you sample a high resolution grid too low frequency, it'll provide really bad aliasing, which is what we avoid with exponential shadow map. That's the first step. Calculate density and light for each cell, or first real step. The third step, or second real step, is to solve the scattering equation by brute force marching through the lighting and density volume to calculate in-scattering and transmittance for each cell. This is very similar to other screen space marching techniques, except we're actually marching in volume space, and the output we calculate for each depth slice and store it in that slice in a 3D volume. So you can see the early slices have very little fog contribution in scattering, but the later slices have more in scattering, less transmittance as you traverse the fog. Kind of hard to visualize, but later on in the demo, I'll show how that works. The final step of the algorithm is actually pretty simple. You just project the pixel screen space pixel. So you shade the scene before all this, and you project the shaded pixel into the scattering volume, and you sample it to get the in-scattered light and transmittance at that point. And then we simply add the in-scattered light to the base color, and then you modulate the base color by the transmittance at that point in the volume. So yeah, in this example, you can see the trees that are farther away. Hopefully compression isn't destroying the detail too much, but the trees are farther away get grayer. I guess they become the color of the fog as there's less transmittance and the fog starts to take precedence. As you increase the density of the fog, intuitively you can't see as far because there's less transmittance overall. So the nice thing about sampling the 3D volume is that our hardware gives us free trilinear interpolation between cells, which means we don't need to blur the volume or upscale it or anything. So we get that free interpolation, and we can use blue noise to hide uh, the interpolation artifacts if those are too unsightly for you, which again you might be able to see in this picture on the right, but my faith in Discord compression is low. So the code for the sample is on my GitHub. I can link that in the Discord actually right now. And I'll do a demo in a second. So the first link that's on screen. And here's the second link. You can build and run the project locally if you want. And then demo, question mark. I say yes. Anyone have any questions, by the way?
Excited to see it.
All right, here's my demo. There's this nice options menu. I can increase the density of the fog, of the ground fog, which the transmittance gets lower. It's harder to see the trees farther away when I increase it. I can make it super thick and it's really hard to see unless you're really close.
It seems like something's moving around in the scene, or is that my
Oh,
imagination?
you're not imagining it. So the ground fog, like I stated, it is simplex noise, but it's also animated
Oh,
by time. So it's sort of like uh,
Thought that was just Discord compression.
fake wind.
okay. Yeah, I was trying to make sure it wasn't like some weird artifact.
Oh no, it's not an artifact.
Okay.
Um, oh, another cool thing, you can see a fog bow emerging from the sun. It's easier to see if I intensify the ground fog. If I turn around, I can see the sun blindingly bright. And the fog bow created because I use a fancy phase function, a really fancy phase function. I had to download a special program to compute me scattering and then export like 1,000 numbers. And I load that in as a texture to use as the phase function. But you don't have to do that. If you use a simpler phase function, ooh, uh, so if I uncheck use scattering texture, it uses Schlick's phase function, which just has a single isotropy, should be an isotropy parameter. So if I increase this to the max, you can see all the light is concentrated in the direction of the sun. And if I decrease it, if I go all the way down to 0, the light is pretty much perfectly evenly spread throughout the volume. There's no directional component. And if I make it negative, then you get backscattering. So if you look away from the sun, you can see the light scattering backwards towards the eyeball. And like I said previously, the backscattering is what you're observing in a fog bow, like that. Oh, anyone want to see the frog?
Of course.
Here's my
You made
frog.
a frog.
Yeah, I went on Shader Toy, and I found an SDF marcher, basically, that creates a frog. I just copied the distance function, pretty much, put it into my code, and I use that as the density and color of the fog in the spot. And then I animated the frog over time. What else can I show? If I turn the blue noise all the way down and disable frog for a second, you can see the trilinear interpolation. It's like kind of looks a little blocky. I don't know how easy that is to see on stream. But if I turn up the blue noise, it hides it a bit. But as a trade-off, you get noise instead of chunky lighting. Any other questions?
Yeah, can you walk through the code in the main part where you were saying in the beginning where it integrates on every point of the ray, and then uh, see how that relates to the final product?
Are you asking about this part?
Yeah,
Okay, so this is conceptual. This is the conceptual model of volumetric rendering, I guess. But I guess I can show you where that is approximated in my code. So I have this shader, which is computing the fog density and light at each point. I guess what you care about is the marching step, is where we march rays through the fog. This is step 2, or yeah, step 3, I guess, in the presentation as I wrote it. Yeah, so we dispatch one thread for each XY position on the density plus lighting volume, and for each XY position we want to march over through the Z. So think of it like a column of depth that we're marching over. And we're accumulating in scattering, and we're also accumulating density. Luckily, I annotated this with a bunch of comments to remember. So for each step in integration, we calculate all this stuff is just calculating the world position of the current cell or fractal that we're trying to find the in-scattering for. And then we compute the step size because we need no step size, because the step size is not constant. So yeah, if we look at this picture, nearest to the observer, the step size is really small, and it gets larger and larger as you get further away. This can be configured based on what projection you use, and you can also manually adjust it using some tricks. So yes, you have the step size, and then after you have the step size and the position in the current iteration, you need to sample the color and density volume at that position. And you need to accumulate the density by multiplying the density of the current cell by the size of the step that you're taking. So if you're taking small steps, you accumulate less steps. If you're taking large steps, you accumulate more density more quickly. And then we calculate the transmittance using Lambert Law, which is, so Beer is a super simple function. It's literally just e to the power of negative d, where d is the amount of density that we have up until this point stepped through. And then we accumulate in scattering. This is a magic number, don't worry about it. So we multiply the transmittance by the amount of light at that point in the volume, multiplied by step size again, because if you take bigger steps, you accumulate more light. I can show you what this looks like in RenderDoc. Oh, and then we actually store the inscattering and the transmittance at the current cell, at the current slice in the 3D texture. So it'll make a lot more intuitive sense if I just show you how that looks in RenderDoc. So, yeah. Is it possible to make everything bigger in RenderDoc? Okay, that's fine. You can look at the textures. So the first step, like I said, is to create the exponential shadow map to get this texture. Second step is to compute the density and incoming light at each point in the grid. So that can be visualized pretty effectively. So RGB is the amount of incoming light. I step through the slices, you can't see much. Oh, that's probably because I had this thing set too low. Oh, okay. You can see the lights. So each time I press the down arrow, it steps forward in the density and light accumulation volume. So these are single slices. And if I switch to alpha view, this shows how much density there is. So I have a switch to application right quick. I have a cube of fog right here. And that's what you're seeing. You're seeing slices of that fog cube as I step through the volume, and then all this noise looking stuff is literally just that. It's simplex noise. And go all the way to the back. It's super far away, and the fog drops off into nothing. And then the step that you're wondering about, Rox, was the actual ray marching.
Mhm.
So this is also this information is stored in a volume, which you can view the result of. So as I step through it, it gradually gets brighter. This is the amount of in-scattered light I'm viewing the RGB. So this is saying at each slice, it's indicating how much light came from the fog at that depth. And then if I switch to alpha view, I'll go back to 0. So this is showing the transmittance. At step 0, the transmittance is 100%. As in, if there's an object in front of me, I'd be able to see 100% of its color. But as I step through the volume, it gets darker and darker, which corresponds to the amount of light that successfully makes it from the point we're looking at to our eye through the fog. You can see the fog volume. More density means less transmittance through that. As I step through the fog volume all the way, it approaches 0 near the middle where the fog continues. So when to actually apply this in the third pass, which is, you can't really visualize, but we take any pixel and we compute its position inside the 3D volume. We project it. So we project it we have to first unproject it from depth space into world space, and then from world space and then into volume space. And that'll give us the XYZ into this volume. And from it, I can show you the code. So to actually apply the effect, we get the Z buffer depth, sample it, we unproject it into world space, and then then we go from world space eventually to the volume UV space, which is from 0 to 1 inside the UV, inside the volume. We do some transformation to the depth. You don't need to worry about that right now. And then we sample after applying blue noise. So what we get when we sample the volume, is we get scattering info, which contains the in-scattering and the transmittance. And then to actually apply it is this simple computation. And base color, which is the color of the opaque pixel in the back buffer, multiplied by the transmittance, aka how far we had to go through the fog volume to get to that pixel, and then we just simply add in scattering the amount of light coming from the fog.
And these lookup textures, this just to clarify, it's storing the result of remarching from the view position to that that spot in the volume.
Yeah, so we have two volume textures that we use for this. The first one stores the depth and the lighting at each cell. And the second one stores the result of solving the scattering equation, which is just remarching. But we store at each point in 3D space, like you said, so then we can sample it later on at any point and blend between samples and whatnot. Normally, the way this would work, I guess if you're doing screen space ray marching, you do like for each pixel, you start at the eye and you travel to the depth, like the back buffer. But this is different in that we need to compute it for every single point in 3D space. And so if you go up to a tree or something, or I guess I can just show you this view. So this is a total accumulated in scattering, but you'll notice that, whoa, it's been way too much. Okay. Yes, you'll notice that there's some in scattering that you cannot see in the final output. Oh, it keeps changing back to slice 0. That's annoying. So the complexity of marching through the 3D volume is constant. It never changes based on like where you're looking, which is good, I'd say. As it means that if you look up, you know, suddenly you don't get lag because now you can see all the clouds or whatever. But the downside is that this does have limited range. If you want to render clouds with this method, it won't be super great because you would have to have a lot of slices in your volume to get that sort of distance. And with the regular perspective matrix, due to the inverse relationship between depth and the actual Z, you get really bad precision at long range. But actually, I do have clouds.
Is that because of is that not is that only when you're not using like reverse-y, inverse-y methods, or is that
Yeah,
just
yeah,
okay?
that's correct. But we do want to have a well, it's bad kind of no matter what. Even if
Well,
you
yeah, I kind of figured that this method is not meant for large-scale clouds
yeah,
in the
it's optimal
distance.
for close range environments because well, we can't have clouds, both clouds and like uh, nice looking close range environments because your precision's got to be distributed somewhere. Or I guess maybe you could use some weird like depth distribution. I don't know. Try this clouds thing. So yeah, I do have like experimental clouds I can enable. Which you can't see immediately because I need to increase the volume far plane. But if I do increase it to 500, so it is 60 initially. I think I can show you that first really quick. Yeah, so the far plane is 60 for the volume. If I increase it a bunch, you can see the lights flicker when I move back and forth due to aliasing because there's not very many depth slices to distribute. And yeah, now you can see the fog or the clouds. It looks kind of okay, I guess. But the clouds are not very detailed, and also they're like hacky experimental clouds. So yeah, designed to see if it would work, not to look good. Oh yeah, you can see another example of really bad aliasing, even though I'm using exponential shadow maps. I don't know how easy it is to see on Discord, but the
They appear.
yeah, the
They're
God rays.
there is some lovely staircasing going on.
Yeah, if I decrease the
Yeah.
far plane, it gets significantly better.
Oh yeah, it's a lot better. There's some light leakage through the tree, which is
Oh yeah.
unfortunate.
Yeah, that's because exponential shadow maps have really bad light leakage. But generally, for participating media like this, it's okay. It is not easy to notice. And plus, if you're going to be doing this technique, you probably won't use a realistic phase function like this. Use an unrealistic phase function where it's a lot harder to notice the light leaking through because it's not so intense when you're looking in the direction of the sun. So I can use the unrealistic phase function. Can decrease the exponential shadow map exponent to make the fog even smoother, even softer, at the expense of more light leakage.
So I have two kind of high level questions slash comments. This is more just thinking about where this could go. The first is a lot of times with fog, there are currents of air moving through it. And I'm just wondering if this has any hope of being able to show that kind of movement of particulates in the air at any level, like from broad bit, like yeah.
When you
And the
say
second,
current, you mean just like little wisps of fog, like moving at like different rates than other fog?
I was just in response to that quickly. I was just thinking that like if the fog is encoded in a volume and it's not an analytical SDF, then you can simulate your air currents inside the volume. It's going to look kind of ugly because it's like a crummy 64 cubed volume or something, but it will
I mean,
work.
it's a good point.
Yeah, you can
Um,
store pretty much whatever you want in the fog volume.
hmm,
That's how I got the zoop. That's how I get the frog, and that's how I get this. Where'd it go? That's how I get the cube. Uh, yeah,
so
it's really flexible in that regard.
so probably
Yeah,
just you might get not very high resolution, so you're gonna have you can't get that super crisp you know fluid sim, but that's not what we're trying to do here.
yeah,
Um,
a fluid sim would not work in this because if I turn around, all that fog behind me is just it doesn't exist anymore. It's screen aligned, so all the resolution is whatever's on my screen.
so the second question is more just a couple of weeks ago, months ago, we did the atmospheric scattering that did everything on like a global scale. So it was mainly for sun shadows, sunlight scattered in and out of the atmosphere, and it was a whole lot more complex looking, but it only is for the sun going through the full atmosphere, and it doesn't do much else. And I'm like, I wonder, can you combine these two seamlessly? If these two effects seamlessly, and if you have no answer to that, that's exactly why I'm asking.
I would say probably pretty much just apply this effect. You probably lose some realism, like
Ooh, yeah.
interactions between that kind of atmospheric rendering and this. But I would say they combine pretty seamlessly because you can just apply this whole technique like after rendering all the other geometry.
Okay.
If you
I
think
guess you'd
about
have to do this. You have to do this after the atmospheric stuff, though.
if you think about a light transport system in the atmosphere in real life, it does all of the regular Rayleigh atmospheric scattering, and then it hits like a massive cloud of dust. That's what clouds are. Before it gets to the Earth. So this fog can totally be at home inside an atmospheric scattering system, I think, because it's just another layer of scattering
Okay.
inside the overall.
Yeah, the nice thing about this technique is the fact that it's really flexible. You can add light to it fairly trivially. It only took me like a night to add lights to this. You can add shadows to it easily. That also took me not very much time to figure out. Yeah, you can put any shape you want in the fog, as I've demonstrated. And hopefully it's not too hard to comprehend how this works, assuming my explanation was successful. I can show you another weakness. So due to the fact that this is only for optimal for simulating low frequency fog, I have softened the edges of all these SDFs. So I can try to lower the softness of, say, the fog cube or the frog. And they should have hard edges. Oh, I'm inside the frog right now. So now you can see some pretty severe aliasing on the fog, or the frog. Or at least I hope you can see that through all the compression. Looks like it's jittering severely.
Yep, we can see it.
Yeah. And similarly with this cube, it's actually a lot more subtle. But you can see staircasing artifacts a little bit. If I turn off the blue noise, it's a little easier to see. But as I go further back, it starts
Yeah,
to
there it
flicker
is.
and
They
so
all
on.
start to flicker.
Yeah, that's all of them. Yeah, that's just due to the fact that the lights are relatively high frequency. So like right at the center of the light is where it's brightest. And so yeah, it starts sampling sometimes the center of the light and sometimes not the center of the light. You get that flickering aliasing. But if you go close, it's a lot harder to notice. So yeah, if you're gonna apply SDFs to this, make sure you smooth the edges or you get chunkiness.
Chunky frog. How many hours would you say this demo took you to put together? Like from understanding the paper to implementing it to adding all the various fun effects you have.
The effects were probably the quickest things to implement. Just getting the core algorithm, understanding that took a while. I can't remember how long because I first implemented this like 6 months ago or something, and then I forgot about half of it, and then like a month ago, I started implementing it again as a demo, but with more features. I guess I can look at my commit history. So 18 days ago, added volumetric fog with volumetric shadows. That was mostly copy paste though. The actual code for this is not super long. You can see the longest shader is the one where I calculate the cell lighting intensity. That's mostly the big chunk at the bottom. It's just some simplex noise function that I copied. That's about 70 lines. It's almost a third of this whole thing. And then the main function is just like clouds and all the effects that I want. Actually marching through the volume, it's a 50-line shader. Applying it, another 50-line shader. The CPU code is oddly organized. The whole thing, about 200 lines long, loading the shaders, updating uniforms, which is absurdly long, actually dispatching to like accumulate density and so on, really short functions, marching the volume, another really short function, applying it, it's just this. So overall, if you actually understand the effect, probably take you like a couple of days to implement.
I just got it working.
But if you're me, it would take me like a week to implement.
What do I press to get into the I am GUI menus? Like my
Oh,
mouse is
yeah, you press the grave accent key or the tilde key.
okay.
Is that the name for that backtick?
Backtick,
Grave
grave accent.
accent?
All I know is that for GLFW, you type GLFW, actually, I'll just control F it.
Mm,
It's called the grave accent in
mm.
GLFW.
French. It's a grave.
Oh, no, it's grave, dude. Someone died on like, part of my keyboard. No, it makes a lot more sense though.
Pretty cool.
Yeah, so play around with that. I'm glad it actually compiled on someone else's computer.
Yeah, it's pretty straightforward. You just have to copy all the assets into the executable folder, like models, textures, and shaders.
Oh, did that not work the first time?
Yeah, no, but that's pretty normal standard. Like they all kind of usually need that.
My CMake must have failed because it's supposed to copy all that stuff for you.
It probably works on your machine because you already did it manually and never bothered to check.
It
I've
worked
done that
on my work
many
machine when I
times.
tested,
Well,
so I don't know what the heck happened.
let's not try to debug CMake right now.
Yeah,
Tis a silly time.
this project also doesn't compile on certain like Clang plus like certain Linux distros because um, I'm like including what's it called, C standard int, but I'm using like uint32t like that instead of saying stud uint32t, and so
God,
the
compilers, stupid compilers.
yeah, you're not allowed to do this unless you specifically include standard int.h or whatever. But hey, it works on my machine.
It's like the classic developer thing. Works on my machine.
Yeah.
I do it all the time.
What's really fun is when it works on your machine, then you push it to CI and it fails in CI. And so you look at why it's failing in CI. You fix it so that it doesn't fail in CI, and now it breaks on your machine.
Oh, I know how to fix that by not having CI.
You just add the test case to the ignore list.
Yes. Because CI is not a real computer.
Yeah.
What matters is in practice. CI is theory.
Practical development tips coming at you hot off the press. Um, I appreciate that all the frog variable names are FWOG.
Oh, yeah, that's because this is actually a sample for an OpenGL wrapper that I made called Fog. And so the namespace is Fog.
Wabbits.
270 or 267 instances of it in this file.
The fact that you're doing atmospheric fog with the fog framework is too perfect.
Yeah. That's why I like to stylize it like that, like how I did in chat.
Have you done any performance analysis or
Yeah,
profiling?
I have, in fact. I should have talked about that in the talk. Let me just scroll up to where I actually looked at this in Insight. But yeah, on my 3070, my RTX 3070, this whole fog, all that runs in 0.7 milliseconds. 0.7.
At what resolution? Oh, is it a resolution independent?
Yeah, so
Okay.
the volume resolution is 160 by 90 by 256, which is double the number of depth slices uh, recommended by the original presentation. And remember, again, this is on much powerful hardware than what they had uh, for the original presentation.
Hmm.
On consoles, they only had 64 slices, and it took like, on like last gen consoles, it took like a millisecond to render.
You know what the reasoning behind the 160 and 90 parts were?
Oh yeah, so you want it to match the aspect ratio.
Oh,
Um,
right, 16 by 9. Yeah, makes sense.
yeah, otherwise these pixels would be rectangles
Mm,
in screen space. I guess I could, let me just do the wrong resolution, 80 by 90. See how that looks. Um, well, it looks really chunky. Oh yeah, that's because it's very hard to tell. Hold on.
Probably
Can
one
you
of
do
those things where it's like inaccurate, but maybe not easy to tell.
could you do like 159? Maybe if there's you know, make the phase make it almost in phase. Oh, that's the extent. Okay. Never mind.
It'd be almost impossible to tell if it was
Okay.
159 because
Because
it's linearly interpolating between
yeah,
yeah. So oh okay, yeah, you can see it's like long. Uh,
some wide lights.
if I turn off the volume noise, oof.
Ooh. The reason I was saying 159 is in audio when you have two pitches that are right next to each other, like 440 and 442. They're slightly out of phase, and they'll go in and out of phase slowly, and so you can hear it coalescing and decohering over time.
Oh yeah, I
And
think I know what you're talking about.
they're called beats, and it's pretty easy to hear even for like someone who has absolutely no music training, whatever. You can hear it if you are given a sample because you're like, oh yeah, there's like a beat pattern going da 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 da. um, just because of it's basically an aliasing artifact, where the two waves combine and in extend accentuate the peaks and valleys.
Have you seen that thing where they have multiple pendulums going at like different length or something, so they go at different, they oscillate at a
Ye-
different frequency?
Yeah, it's exactly like that, just auditory, not visual.
Yeah.
Have you seen the ones where they're on a slightly wobbly table, and after a while, all the pendulums, or like metronomes, is what I'm thinking of. All the metronomes start aligning. This is getting slightly
On
off
a wobbly
topic.
table?
So the effect is that it synchronizes over time due to the everything is there's like a slight preference to shifting at one time, and so everything over time wants to be in phase with that because that's the most energetically conserving pattern. And it's fascinating to watch because it's like two completely chaotic systems will start syncing up just because they have just a bit of wiggle room to interact with each other, even if only a couple of millimeters.
Interesting.
Oh yeah, I've seen that. That's
Yeah,
weird. That's interesting.
yeah. I think there's a Veritasium video about it. There's other things online too.
They did that on a bridge or something with the metronomes.
Oh yeah, that, yeah, that would work. Um, okay, yeah, we're slightly off topic.
I finally found the Insight picture that I took showing the performance of this. So you can see in purple, if you expand the picture. Actually, I can just show on my screen. So the purple, the first dispatch is the accumulation of density and lighting. Actually, it's an older version where I just had density in this pass, 0.27 milliseconds. Ray marching, 0.31 milliseconds. And then applying it was like so tiny, 0.05 milliseconds or something. So overall, it's super duper cheap.
I was thinking about the question of combining it with the atmospheric scattering some more, and I feel like this could be wrong, but it seems like you might run into some issues with that because with the atmospheric scattering stuff, when you're rendering all the objects, they've already done all the like extinguishing and in scattering and out scattering. So then when you are going, so that includes like all the path from the view to the object. So if you then add this on top, I think you'd be like you're starting with something that's already been scattered, and I don't think that would be accurate if you added this on top.
Mm.
Yeah, it feels
Yeah,
like
that only
the
took a
same
long
thing.
distance.
It's like trying to do some of the same thing.
Yeah, like you would really want this to be like both scatterings to happen at the same time, like calculate the atmospheric and this at the same time. But so much of the atmospheric stuff relies on all those offline pre-computed stuff, so you wouldn't be able to use any local differences in fog.
Yeah, I think the difference between ground truth and like what you'd get if you just combined volumetric fog on top of atmospheric rendering, I think the difference would be really small and hard to notice.
Yeah, you're probably right.
Particularly because you use this fog for rendering close range fog, and so you'd mostly be looking at nearby objects. But even if there's like a mountain or something behind a volume of fog, the incorrect color, I feel like it'd be so hard to notice that like, oh, it's it's a slightly wrong shade of blue due to Rayleigh scattering.
Yeah, it's probably negligible in practice.
Are you talking about this picture? Oh, I think I see what you're saying.
Yeah, because I guess if you like you're saying like start from the far plane of this and then do the regular atmospheric stuff for the rest of the distance that's not covered. Right, yeah, because the typical atmospheric scattering from you till your first far plane is probably gonna be very small, so you might be able to just ignore it for that. That's interesting.
Just put a link there. Is that the paper that you worked off of, Jaker?
Oh yeah, let me link that.
Okay, cool.
This is not the primary one that I use.
Okay.
Oh, here is the good paper. Oh, and here is the original presentation that has a bunch of other stuff in it, like global illumination and post-processing.
Cool. Thanks.
But the first one I linked is basically the same thing, but just the volumetrics part and also expanded upon it. And also it's really similar to my presentation. Oh, meat plot. What about it? Oh yeah, meat plot is ridiculous. Um, I had to help someone or have someone guide me through how to use it because that program is complicated. I can't even remember where I installed meat plot. Oh, I found it. Oh,
Water in a vacuum.
this is some OG software. And yet they still update it. Yeah, like here's an example of one of the outputs of meatplot. And so I had to take something like this, save the numerical results to a file, put it into Google Sheets, and then normalize it so that if you add up every point, you get one, and then turn it into a texture. Or I turn it into a texture at runtime. I can show you what that texture looks like. In fact, one-dimensional texture called fog scattering, where UV0 represents or corresponds to looking directly at the light source. You're in line with the light source, so the dot product between the I vector and the light vector would be 1. And then, oh yeah, and then a UV of 1 corresponds looking directly away from the light. So this would be like backscattering over here. And you can see where the fog bow appears at this band that I'm highlighting.
So what you're saying is you could custom author this texture to say to be very not realistic and make it look very funny.
Yeah, you could put whatever wacky pattern you want in it.
It's one-dimensional and it's radial, so I don't know if you can make it anything more than just a bunch of circles.
What was
Um,
this one? What was this one representing?
oh, this one? This is like fog or something. Oh yeah, yeah. So the UV corresponds to the dot product of the angle between the I vector and the light. So over on the left side is looking straight at the light. You can see it with forward scattering. It's most intense on the left when you're looking at the light. Whoa. Oh, that's way too. Well, I need to increase this or decrease this. So yeah, it falls off as you look away from the light, which you can see. I think it's pretty intuitive. I'm looking at straight at the light, so I'm sampling the leftmost part of the texture, and as I look away from the light, the I vector goes away from it. I sample like the middle of the texture where it's dark. But then once I get to this point, over here is band. I turn around, you can see the fog bow. The beautiful fog bow. And right in the middle, this thing is called glory, apparently. And this corresponds to a really tiny band over here on the right.
Oh, wow.
And so, yeah, pretty much this texture is a visualization of a phase function.
Which phase function? Like, is it like is like what did you put into Meatplot to get this one?
Wait a sec, I got a interruption. Okay, I am back. What did I put into Meatplot to get this? That's a good question. I can remember it though. I just need to remember really hard. So yeah, you want intensity versus scattering angle. You want me scattering. Yeah, you want whatever the setting is. Gamma. And the light source should be the sun, I suppose.
Okay. This is a very interesting program, and
I can't remember what shape K and N are supposed to be.
What
Oh,
is
maybe
the the title text? What's the hover text say?
what
The
for?
K and N.
Oh, N is number of samples approximate statistical distribution. I guess you want that to be fairly high. But I'm gonna run a test. I better make it low so it doesn't take forever. K is standard deviation of the drop radius, percent of median radius.
Okay,
And
I don't understand.
that will be because these bumps are probably approximated with Gaussian curves. I think that are multiplied with the rest of the function. So the standard deviation is like the tightness of the curve then.
Oh yeah,
That
makes sense.
makes sense.
Yeah, this is haze. Interesting. I've not tried this. Oh, cool. It simplifies things. Angular resolution. Sure, if you just press enter, it'll start simulating. Whoa, this looks different.
Is this for like, is haze a specific algorithm or is it like a description of the
It's a
type of?
description of a particle that's being suspended in the air.
Yeah, because when I imagine haze, I think like a highly polluted urban area with a bunch of car exhaust, but that may not be what that is.
Maybe. Sorry, what's that? Oh, yeah. So if you want a fog bow, you need to look for a spike, just like this one, a dip followed by a spike in the graph.
The perturbations that are much smaller in frequency are interesting. Like at the 30 mark on the bottom axis,
Oh,
there's a,
yeah, I don't know what's up with these.
yeah,
But you can go to File, Save Numerical Results. Uh,
mm,
and you open it, you should get a text file with a lot of entries. But the one you care about, you want to scroll down to where it goes angle, wavelength, perpendicular, parallel. Um, yeah, and just click right there, scroll all the way to the bottom, and shift click, and copy that into Google Slides. Or no, Google Sheets.
yes, I want 180, no, an 1800 page PowerPoint where each slide is just one row of this data set.
Oh yeah. And then I think you want the parallel data, not the perpendicular. Then you just need to take the average of a category.
5,400. It's a lot.
Yep. Yeah, it's a lot. And then to normalize the data, you just need to divide
Oh, by the average.
everything. Yeah. Or, yeah.
Don't you want to divide it by the max value?
You want to divide, wait,
That just makes it relative to 0 to 1.
hold on.
Right. Yeah, you're not saying integral, not the actual values. Right.
Wait, are we?
Wait,
Yeah,
no, don't
yeah.
you?
I guess we are. I guess I was thinking like normalizing, like taking a 2D vector and making it unit length. Whereas what I think you may, what it really, yeah, I think you're right.
You
Hold
want to
on,
make the sum of it add up to 1.
that's very different than just making it range from 0 to 1.
Yeah.
Yeah, yeah.
So there's some trick in Google Sheets to like apply a formula to a whole column.
I mean, you can drag it, but that's gonna take a while.
5400. Oh, and I got division by 0. Oh, because it's smart, usually.
What if you right click it does anything up? Oh yeah, you could just Google it.
Oh, I've Googled this before. Shift click on the last cell to copy to control. Oh, click on the cell with the text format to copy. Shift click on the last cell.
Oh yeah.
So click, shift click. Wait. Oh, control enter. Yeah, so that was step 3. And then you take all this data, you put it into a file. So I have this one called textures. Paste, save. And then I need to actually load this. And it crashes. Excellent.
How's the? Is it in the right folder? Oh, it's too many lines.
I believe so. I'm hoping it was too many lines. That's the problem. Oh, it was. Oof.
Ooh,
You can see, I think these are the dips that you were talking about.
yeah.
That
Ouch.
I think that's because,
And they're like colored too.
yeah, number of samples is too low. And so you can see like the outliers. Yeah, they're colored because this is a dip in red.
Yeah, and there's a dip in green and then a dip. Oh, look at that. Look, it's blue, green, red, the dips. And
Yeah.
that would follow a each wavelength being smaller than the last kind of thing. But only the red and green are big enough to be very visible.
Make the fog.
Oh, that's bad.
I can see
Well,
red. I
it
can see
looks
kind
more
of blue
cyan
green.
purple if you ask me, but
Well, in theory,
yeah.
Oh, okay, so when it's missing
Oh,
red.
that
Wait,
looks
no,
yellow?
interesting.
I think it's because the red is gone, it gets the blue and green and gets cyan or whatever the combination of that is. Yellow? Yeah, this looks
Blue.
like a CYMK plot. Is there another divot between the red and yellow? Yeah, there seems to be like a fourth line.
Green to red and yellow. Oh, yeah, it shows up, but it's like aliased, so it's kind of hard to see.
Are there just more dips that we are not seeing? Or
Um,
strange.
I go way down. Yeah, no, I can see yellow, purplish, cyan.
But how many dips are there? There's
It's just,
another, well, once it gets to, yeah, there it's just
it's
wavy.
really dippy. So if I look to the side, I might see, look to the other side. I can see some bands here.
The Discord compression just makes it look like a JPEG.
Yep.
Uh, the banding. Oh
Or
yeah, that looks like camera lens artifacts.
I just use an analytical phase function. You don't get any of that. Or if you, sorry. Oh, I have not tried that. I did read about that in the original presentation. Mm. Yeah, I just didn't know how to construct. I'd take a weighted sum of them. I actually have a. Oh god, too many tabs. Oh, I need custom. Uh, so let me try combining multiple HGs. Oh, whoa. What the heck? I see. I wonder what this would look like. No, the forward scattering would be negative. The back scattering would be. I guess it shouldn't be negative. I guess it doesn't make sense for the value to be negative. You usually have to clamp it. Get some interesting shapes with this. Oh, and let me share my slides in Discord. Oh, yeah.